My name is Eric. These days I'm with the AWS security team, but when I joined Amazon 8 years ago, I was with the team that defined and launched VPC, and that's what we're going to be talking about today. That clicker works. So this is a reprise of a version of this talk that I gave at reInvent 2 years ago. I'd like to manage expectations. A lot of the content is the same. There is some new stuff, but if you're expecting a completely new talk, I'd rather you leave angry now than leave angry at the end of the talk. The problem that we're trying to solve with VPC is simple. We're AWS. We have the cloud. The cloud is full of all sorts of AWS-y goodness, services like EC2 and Elastic Load Balancing and the Elastic Block Store and our relational database service and Amazon Redshift or Columnar Data Store and Elasticache. Customers have data centers. These are data centers they've owned for years. They're expensive capital investments. They're not going to go away immediately. And so, as good engineers, we go to the whiteboard and we draw an arrow. This is what we wanted to do. We wanted to plug customer data centers into the cloud. This is going to be a really important deployment scenario for us. We have customers, you hear stories about Netflix and customers like that are all in on the cloud. They're closing their last data center. But for every Netflix that we have, for every customer that's ending that journey, we've got another customer beginning that journey. So as a service provider, we are always going to have customers that are running hybrid operations between their existing infrastructure and their new infrastructure in the cloud. And it's unrealistic and unwise to expect people to do big bang migrations. It's going to be applications moving gradually, data moving gradually. So in order to win this business, in order to do cloud right, we're going to have to support this for the long term. So at the first reInvent, we had a talk entitled Drinking Your Own Champagne by Laura Grid. It's available on YouTube. I highly recommend it. It's about Amazon's own story moving to AWS. We are an enterprise just like many of you. We had data centers. They were built to serve our needs. They were built without considering a future move to the cloud, and we had some challenges there. VPC was critical to that adoption. It was one of the major building blocks that we used. And this is a story we've seen unfold with a lot of other customers. So in the beginning, we had EC2. And when you launched an instance, we would sign an IP address to that instance. And it was effectively a 32-bit random number. It was unique in the cloud. You'd get a DNS name. You could route traffic to it. And when you launched another instance, you'd get another IP address. And it was another 32-bit random number. And meanwhile, there were other tenants. The cloud is multi-tenant. There are other customers launching instances in the cloud. And we would assign them 32-bit random numbers as well. And this would go on, and everything was great. Now, we come to a customer data center. And let's say that someday, 20 years ago, 10 years ago, whenever this data center was built, some network engineer chose 192.168.0.0/16 as the IP range for the data center. A perfectly reasonable choice. So there's a router there. And this is a router, like a piece of sheet metal. It comes from one of the major router vendors. It's got some embedded firmware on it, some TCAM, and it's got a routing table in it. And it says 192.168, that's here. So if we're going to plug that into the cloud, if we're going to plug that into the EC2 network that we had, well, you're going to launch an instance, and we're going to need to route to that instance, so we're going to have to add it to your routing table. But we have to add a /32 route. We have to add a host route, because the next instance that launches, right next door, the next IP address could be a different customer. You don't want that instance routing back to your data center. So as you launch instances, we have to add them to the routing table. And as you terminate instances, we have to make sure that you remove them from the routing table. So your routing table is going to, one, contain a set of routes the size of your instance fleet, not good, and two, your routing table is going to absorb updates at the rate of instance launch and terminate, also not good. But that's not all. Let's say that a decade ago, your network engineer chose 10.44.0.0/16. An equally reasonable choice. It's RFC 1918. It's not going to be routed on the internet. There's absolutely nothing that we can put in that routing table that'll make sense. We've got 10.44 in the cloud. We've got 10.44 in the data center. You can do things like double NAT. If you ever say double NAT to a network engineer, make sure that you're standing far away from them. Like this horrible network design. So we've got a problem here. So from a customer-facing perspective, we have customer-selected IP addresses. Customers want to bring their own IPs. You have a network. It has some design decisions that were made years ago. They're not good or bad design decisions. It's what you have. It needs to work with our stuff. We need route aggregation. Your router, you can try this if you want, but I guarantee you your router will be sad if you add and remove route updates, if you add and remove routing table entries every time you launch or terminate an instance. So we need some way of aggregating this so that routing table updates are infrequent. They happen when there are network configuration events or network connectivity changes. And we need conformance with existing network designs. This was a fun conversation that we had internally. We want to build a beautiful new abstract cloud network. And I was arguing that no, actually, customers have a preconceived notion of how networks go together, and you need to conform with that. You need to meet them where they are. You need to allow them to photocopy their existing network designs through our APIs. And then we had an early customer who happens to be sponsoring this conference. And they came to us and they said, all networks have to be /24s. Our provisioning tools can't deal with anything else. And that solved the case for me. Amazon's own data centers, which are amazing. Like, we were very, very good at automated data centers, automated provisioning, scale, and all of that. The tools there were built by us to work in our data centers for our provisioning use cases, and all of our subnets were rack size. They were all /24s, and we just assumed that all networks forever would be /24s, which was the right decision to make. When we built those provisioning tools, we never thought about the cloud. And so my own company helped me sell the idea to my company. It was a nice turn of events. So the high-level presentation is, you have a data center. It has some arbitrary network range that you've chosen. You create a VPC. This is an API call into our control plane. And when you create the VPC, you specify the CIDR block you want for the VPC. So this customer's chosen 172.31.00/18. It's an arbitrary choice. It's up to you. It should be something that doesn't overlap with anything else you want to plug into it. Then you create a VPN gateway. This is our end of a private connection. You create a customer gateway, and we don't yet have APIs that cause routers to pop into existence. This is more telling us about the device on your side. So you give us the IP address and things like that, and we know now what the far end of the VPN connection is. And then you configure a VPN connection. It's done programmatically. On our side, we give you the router configuration you need to install on your side, and now network connectivity can come up. And your router is going to learn a route for that VPC, one route that covers the entire VPC. Within the VPC, you can allocate subnets. The subnets have to be within the CIDR for the VPC itself. You can create as many of these as you'd like. And now, as you launch instances and terminate them, there are no changes to your routing table on-prem. So we've solved the overlapping IP address problem, and we've solved the high-velocity routing table update problem. Why am I telling you about this? This is a solved problem. We've been doing this for decades. Like a subnet, you're using these fancy cloud terms, but it's just a VLAN. Like, I know what this is. Not as many people know about VRFs, virtual routing and forwarding. It's the same thing as VLANs, but for layer 3. You fragment your routing table into multiple virtual routing tables. So you take the smart, complicated physical network that you've used for years, and you ask it to make virtual copies of itself. This is a mature business. It's used in data centers all over the world. But our application is not the same as those applications. The VLAN header. Perfectly reasonable thing. No one thought that 4096 was going to be a constraint. We publicly talk about how AWS has more than 1 million customers. 1 million is larger than 4096. Even more concerning, like the 4096, that's easy to test. Like, it's a 12-bit field in the header. You can iterate through all of them. VRFs are complicated. And most vendors haven't actually tested beyond 512. We know, we tried. But even if you do go beyond that, large, like blast furnace full rack routers, the things that cost more than your house, support 1,000 to 2,000 VRFs. 1,000 to 2,000 is still less than 1 million. If you're buying a device that claims to support more than 2K VRFs and you are intending to use more than 2K VRFs, you are a beta tester. This is not what we want to be building our production services on. And there's a fixed ratio of VLANs to VRFs. You get 4096 VLANs on a port, you get 1,000 VRFs in the box. What if your customers want more than 4 subnets per VPC? What if they want less? You're going to be stranding some resources. But that's not all. We're talking about these giant blast furnace routers, and these things are fast. They are amazingly capable. But we're talking about the data plane here. These are custom switch ASICs, the fabric cards. This is the fast part of the router. Inside the router is a control plane. Many of them are actually x86 boxes running FreeBSD or Linux these days, except they have less RAM and less horsepower than this laptop, and they cost as much as a car. And it's connected to the data plane via a straw. You've got a data plane that's got 110 gig ports, and the control plane is going to have dramatically less connectivity there. It's the control plane that's dealing with all of this configuration complexity. And the way you scale these things is you do 1 + 1 failover. But it's failover between the control planes. So we loaded this up. We actually did this. We had a pair of routers, and these were amazing routers. Like, you could push terabits of capacity through them. But when you failed one of the routers over, the control planes would go dark. There was actually one router brand where there was a watchdog timer. The control plane went dark so long trying to reconverge all of the routing protocols that this one rebooted. So then this one came up and tried to reconverge all of the routing protocols and rebooted, and we just had routers seesawing back and forth. So these routers are configured using text files. If we figure an average router config line is 50 characters, it takes us 10 lines of router config to describe a VPC, a VRF. Figure an average of 4 subnets per VPC. It takes us 5 lines of router config to describe a subnet. And we've got 2,000 customers on the box. It's a 3 megabyte text file. Committing one of these configs on one of these routers, literally it could take it 3 to 5 minutes just to parse the configuration. Not to apply anything, just to parse the configuration and validate it textually. These routers are just computers with strange hardware. They have the same bugs that every other system has. The software is written by humans. Humans write all the bugs. And so there are assumptions in these routers. And they work really well for their design point, but they work really poorly if you use them outside that design point sometimes. For example, we had a device that we were using, and it was a similar use case. We had a lot of a certain kind of config, where the typical, you'd have like a dozen of these, and we would have thousands or tens of thousands of them. It turns out the internal implementation of that was a singly linked list. So if you wanted to add one to that list, you had to chase pointers all the way down to the end of the list. If you wanted to delete one from the middle, you had to chase pointers until you found it and stitch it out. When you have 8 of them or 12 of them, no one notices this. Computers are fast. When you have 10,000 of them, all of a sudden the control plane starts to fall over. There's another problem we found with a device. Every time you committed the config, it would leak 2 words of memory. Well, how often do you commit config on a router? Like a dozen times when you're building the thing out, maybe every couple of months when there's a network design change, you add new capacity. We commit config to routers every time customers make API calls. You want a VPC, you want a new subnet, we're going to be committing config. So we exhausted memory on the control plane due to this memory leak. It had been present in the code for like 10 years, and no one had found it until we did this. It's because we were operating outside of the common envelope. We'd become beta testers again. So this doesn't scale. It's going to be expensive. The closest I have come to career suicide was when I proposed this design in front of a bunch of network engineers at Amazon. I swear to God, one of them was in the back of the room sharpening a big knife. Like, this is not the way to make your network engineers like you. We're tied to vendor bug fix cycles. If you've got something that goes wrong in your data center, it affects you. And we have something that goes wrong in our data center, it affects all of our customers. And it's likely to affect multiple devices in our data center because we keep cookie cuttering out the same design. We like to control our own destiny. We like to be able to fix things on our time scale. You know, that memory leak bug that had been present for a decade, it's not a high priority bug for literally any other customer of that vendor, but it's super high priority for us. And that impedance mismatch causes problems. And so we want to be on the commodity curve. We want these things to be getting cheaper as quickly as our compute and storage are getting cheaper. And a lot of the selling points for these large vertically integrated devices is all sorts of advanced features. But the interoperability of those advanced features is pretty poor, and we don't care about them. We want the network to be fast and dumb. We want it to pass the bits. We don't want the fancy features. We don't want to pay for the fancy features. And I keep saying we horizontally scale. We stamp out multiple of these things. But this isn't horizontal scaling. It looks like horizontal scaling because there's two similar things sitting next to each other, but it's really silos of capacity. So we've got routers, and because I got tired of making boxes in PowerPoint, each router can support 4 customers and 40 instances worth of capacity. And so customer A shows up and asks for 3 instances. We arbitrarily choose to place them on the left silo. Customer B shows up, arbitrarily place them on the right silo. Customer C, like there's some sort of load balancing placement algorithm going on here. And as launches come and go, we add them. Now, customer A just launched 2 more instances. Because their VPC is hosted in the left silo, I have to place them in the left silo. That placement decision is made for me. Customer E shows up. It's 1 instance, looks puny. This is an incredibly important customer for us. This is the Getting Started guide. Every single one of our customers was once a 1-instance customer. This customer may get off the platform tomorrow and we may never hear from them again. They may be the next Netflix. I don't know. F shows up. This is a large enterprise customer. This is a planned migration. Maybe we knew how much capacity they were going to need, and we could make an intentional manual decision here. Customer G. I just allocated the last customer on that left silo. It's full. I've got a bunch of capacity available, but I can only sell it to those 4 customers. Now, obviously, in the real world, it'd be a lot more than 4. You'd get better statistical averaging. But still, I'm stranding some capacity here. And I can hide that by increasing prices. If I get 90% utilization out of the fleet compared to what I used to get, 11% higher prices, and we're back where we started. We just announced our 50th price decrease. Pitching products at Amazon that cause things to get more expensive is not a good path to success. So this is bad, but this isn't the worst. Customer B is some sort of social media application, whatever the kids are using these days. I've stranded some router capacity there, but that's nowhere near as bad as the fact that I've exhausted my instance capacity. I can't hide this from the customer. Customer B wants 1 more instance, or even port D and F, who have no idea that they're co-located with B. I have to expose that to them. They have to go create another subnet, or they have to create a new VPC. That's an unacceptable customer experience. So to do this internally, and this is actually a line from our original design doc, we want to support millions of environments the size of Amazon.com. We must not further constrain the placement problem. Any instance anywhere can be in any subnet in any VPC. So to do this, we've got servers. Someone has to be the bottom turtle. We're the ones that own the sheet metal. So we've got a physical network with physical servers. On those servers, we place instances. Those instances are grouped together into VPCs, virtual private clouds. In our APIs, VPCs have identifiers, VPC-8 hexchars. I also got tired of typing those in, so I used colors here. So we've got 3 VPCs running around in this network. And then the mapping service. This is a piece of VPC that's not exposed directly to customers. The mapping service is the linchpin around which everything revolves. So these are the basic building blocks. This is layer 2 Ethernet. This is how Ethernet has been working for decades. It comes off the operating system DVD, or I guess whatever it is we use to distribute OSs these days. 10.0.0.2 wants to talk to 10.0.0.3. He's going to ARP. Last time I gave this talk, I said I'm using this MAC of IP address notation because typing in MAC addresses is arduous and it's hard to remember which MACs go with which IP addresses. And I said, please substitute your favorite 48-bit number. One of my coworkers kindly pointed out that not all 48-bit numbers are valid MAC addresses. So please substitute a valid 48-bit MAC address. Hi, Andrew. The Ethernet switch doesn't know where 10.0.0.3 is. Let's pretend everything is freshly booted. So the Ethernet switch is going to flood that ARP request out every port, including the port that happens to have 10.0.0.3 connected to it. 10.0.0.3 is going to respond and say, hey, that's me. We're going to learn the MAC at the switch, and the Ethernet switch will forward the response. So now 10.0.0.2 has managed to learn the MAC of 10.0.0.3. The switch happens to have programmed its CAM. And so now we can send some sort of IP packet. The L2 and L3 source match, the L2 and L3 destinations match, the Ethernet switch forwards it across the network. This is happening, I don't know how many trillions of times a second all around the world. That's what we have to make work. So 10.0.0.2 wants to talk to 10.0.0.3. He's going to send that exact same ARP request. We're going to trap that ARP request, and we're going to send a query to the mapping service. And we're going to say, hey, we're looking for blue 10.0.0.3. Mapping service is going to tell us where 10.0.0.3 is. We learn the MAC, but we also learn the physical server on which blue 10.0.0.3 lives. And we form an ARP response and propagate it back to the guest. One interesting wrinkle here, that ARP request never made it to 10.0.0.3. You can do this today in VPC. Spin up an instance, run TCP dump, you'll never see ARP requests. It turns out you don't actually need to see the ARP requests. It totally doesn't matter. So now we can send that packet. It's the exact same packet we're going to send across the physical network. We're going to trap that packet. We're going to wrap it with a VPC header. It's tagged to the blue VPC. We're going to wrap it with a physical network, a substrate network IP header, and we're going to send it directly to the server that's hosting blue 10.0.0.3. On receipt, we're going to ask the mapping service, hey, I just got this packet from someone claiming to be blue 10.0.0.2. What's up? The mapping service is going to say, that's cool. And I didn't draw it here in the slide, but this is how we fill in the MAC address for the source at receipt time. And then we can deliver this packet to the guest. So this is it. This is the Ethernet stack. This is layer 2 packet forwarding within a subnet, working straight off the OS DVD. We didn't have to change anything in the instances, Windows, Linux, whatever. It just works. In order for these two instances to communicate, the only requirements are they have to have direct IP connectivity to each other, and they have to be able to talk to the mapping service. We know how to build networks that span data centers, that span the globe. So we've succeeded here. We have not constrained the placement problem. Any two physical servers can host a pair of instances in any subnet, regardless of their placement on the IP network. So the virtual L2 topology is completely decoupled from the physical topology. So that mapping check on receipt, let's dig into that for a moment. So let's say that for whatever reason, Gray 10.0.0.4 wants to talk to 10.0.0.3. We're going to send a query to the mapping service, but it's going to be tagged to Gray. You have full access to the IP headers and the packets you generate. You can fill in any 32-bit destination address you want. We will always interpret that in the context of your VPC. And so you can literally scan a /0 from within your VPC, and unless you have routes to them, you can't talk to instances in other VPCs. Via some means, we've got a corrupt mapping, something has gone wrong here. We're going to send this query, and it's tagged to blue. So we claim to be from the blue VPC. The mapping service knows that there aren't any blue instances on that physical server. This is an errant packet. It should not flow. So we're going to deny that mapping. We're not going to tell the source where that destination is, and we're going to call a human. If, via some means, we manage to obtain the mapping, and we send the packet across the physical network, on receipt, we're going to do that reverse mapping check. We're going to say, could you please verify for me that the instance claiming to be blue 10.0.0.4 is really at that physical source? No, it's not. This mapping is invalid. This packet is invalid. So we're going to drop that packet. We're going to call for a human. And what this means is that packets can't flow across the network unless all parties involved, the source, the destination, and the mapping service, agree that the packet should flow. Our control plane has 100% visibility into where every L2 and L3 address is placed in the network. And we can very strictly control which packets flow. So next up is L3. Again, this is straight off the OS DVD. It's the way it's worked for years. In this case, we have, if we assume /24 net masks, we're talking across a subnet boundary. So 10.0.0.2 wants to talk to 10.0.1.3. This is in a different subnet. We have to go through our gateway. So we're going to ARP for our gateway. It's the exact same dance. Packet floods. We learn the MAC. And we learn the destination MAC address. And so now we can send a packet. And in this case, the L2 and L3 sources line up, but the L2 and L3 destinations don't. The L2 destination is the gateway. The L3 destination is the eventual host. We send it to the router. The router swaps out the MAC addresses. Now the source is the router's interface on the right subnet, and the L3 destination is still the eventual box, and we deliver it. This is L3 IP forwarding as routers have been doing it since time began. So we've got the same situation in VPC. We're going to ARP for our gateway. The mapping service is going to tell us it's a special host, it's a gateway. So we get a MAC address for it, but we don't have a physical destination for it. We can send the ARP response back to the guest, thus completing the protocol. And so now, the guest is going to try and send a packet. This is the exact same packet that it would have put on the wire in the previous slide. We stop that packet, we queue it up, and we make a secondary query to the mapping service. And this time, we don't query on the L2 destination, we query on the L3 destination. So we learn that blue 10013 is located in that box in the lower right, 192.168.1.4. So now we can send this packet across the physical network, wrap it in the VPC header, wrap it in the physical header, and deliver it. The exact same reverse mapping check gets performed. We swap out the MAC addresses, deliver to the guest. This, again, achieves our goal. We've placed no further constraints on L3 packet forwarding compared to L2 packet forwarding. Any two boxes that have IP connectivity with each other and with the mapping service can host any two instances in any VPC across subnet boundaries. So this is the system we went with. The system is not without scaling limits, but it's with scaling limits that match our use case. It's designed to match our very specific, very narrow use case, and we own it. We can fix it. We can alter it as time goes on. So I queued this packet. The customer sent it. I snagged it, and I queried the mapping service. So this means that the mapping service is now critical to packet flows. That if the mapping service isn't available, the packets won't flow. And in addition, even if the mapping service is working correctly, there's now two paths through the system. There's a fast path where we've already got the mappings, and there's a slow path where we have to queue packets and query the mapping service. And so in reality, there's a mapping service replica, a little cache, on every single one of our physical boxes. And they subscribe to the mapping service. It's logically exactly the same. We have strict ACLs on all of the records in the mapping service. The cache can't populate records that it shouldn't have access to. We get the same kinds of alarms raised when instances try and fetch the wrong records. But it means that we have a 100% cache hit ratio. We actually did not implement the cache miss path. The only way to translate packets is through this cache. And so that gets us dead flat latency, and it mitigates a bunch of availability concerns. So, new content warning. I've told you how we can talk within a subnet, L2 forwarding, and how we can talk across subnet boundaries, L3 forwarding. But I haven't answered the problem that motivated the entire talk. How do you get back to your home office or your existing data centers? We know how to send the packet. Like, there's a source IP, a destination IP, life is good. We can wrap it with a VPC header, but then what do we put in for the destination? Or if I do put in your VPN router as the destination, it's going to get this proprietary Amazon-wrapped packet and be all confused, drop it on the floor, and your packets aren't going to flow. And so we've got a new kind of thing in the VPC world. We call them edges. We're very creative people. So if we look at the mappings that are cached on this physical server, there's actually two kinds of mappings there. There's /32s, effectively. There's host mappings. This is for talking to other instances. But then there's also routes. There's CIDR mappings. And so we have a route here that says 172.16.00/16, which is the home office or the data center, routes to this edge. And so we know how to do this. Like, you send the packet, we wrap it up, we send it onto the edge. The edge will perform exactly the same reverse mapping checks. It's just another participant in the VPC network. And so what this thing does, if, for example, we're talking down a VPN connection, we send the packet to the edge. The packet is familiar with our virtual networking protocols. It can unwrap this packet, figure out where it's going, and it can rewrap this packet. And in the case of VPN, it's all IPsec. So we've got a system that takes VPC encapsulated packets, determines whether or not they should flow, maps them onto customer IPsec tunnels, and sends them out over the open internet. If you're using Direct Connect, Rather than using IPsec tunnels over the internet, you can get a hardline connection, a fiber gigabit, 10 gigabit connection to AWS. If you're using Direct Connect, we do almost exactly the same thing, except that rather than doing IPsec, we put a .1q VLAN tag for handoff to our Direct Connect router. I complained about VLAN tags earlier, so I owe you guys an explanation. 4096 isn't a lot, but this VLAN is literally that long. It moves from one router in a cage to another router in the same cage. And so we're limited to 4,000 customers per port, and that's not a limitation for us. We reuse VLAN tags per port. So there's also the internet. People like talking to the internet. There's a lot of stuff out there. Send the packet to the edge. This is getting boring. But then what do we do with it? How do we encapsulate it for sending to the internet? And the reality is we don't want to encapsulate it to send it to the internet. We just want IP packets. That's what the internet runs on. And so there you go. If I send this packet out to the internet with this source IP, it'll actually arrive. And the destination will get it, and it'll attempt to send return traffic. 10.002 is an RFC 1918 IP address. It's not routable on the internet. So the host actually doesn't know that. If it's a TCP connection, the SYN packet will go out. The SYN ACK packet will be generated by the server. He'll drop it into his network. It'll fall on the floor. This is an unsuccessful network connection. So we do one-to-one NAT. This is where elastic IP addresses enter the story. So when you map an EIP, an elastic IP address, a public internet routable IP address to your instance, this edge is the box that's performing that one-to-one translation. So on the way out, we replace the source IP with your EIP. On the way back, it's going to be sent to your EIP. We swap out the destination IP address for the private IP of your instance. So we've got a box now. It does packet mangling for us, packet translations. And an interesting story. There's a good-sized chunk of the EC2 team in Cape Town, South Africa, which is almost as far as you can get from Seattle. It's called antipodes. If you put a globe on a drill press and you start in Seattle, the drill will come out in the Indian Ocean off the coast of South Africa. If you go there, you will encounter the African penguin. The African penguin is also known as the jackass penguin because they really do sound like donkeys. But it's also known as the Blackfoot penguin. And Tux is the Linux mascot. So when we built a Linux-based network appliance for EC2, we named it the Blackfoot. So if you hear any Amazon people talking about Blackfeet, it's those edge devices. And it also happens to be the name of one of our office buildings in Seattle. So most of AWS works in the Blackfoot building. So pricing. VPC costs nothing. Subnets cost nothing. And instances in a VPC don't cost any more. And so I mentioned that earlier we had our 50th price decrease at AWS. VPC will never participate in AWS's tradition of decreasing prices. But this is exactly where we want it to be. We can now offer customers a flexible, programmable virtual network at no charge. In addition to being the day after my birthday, this is the day that the last US retail physical web server was turned off. I stole this slide from Laura Gritt's Drinking Your Own Champagne talk. So if you've bought anything, if you've surfed the Amazon website since November 10th, 2010, and I hope you all have, the page you viewed was rendered by an EC2 instance. 100% of US retail pages have been rendered in EC2 since this date. So this is not a research project for us. This is a robust production network. We run our business on it. And we carried Q4 in November. This year, it's going to be the 6th Q4 for Amazon Retail that we carry in VPC. VPC has grown a lot. It's become a platform. So you were always able to get instances in your VPC. But a lot of our services, like RDS databases and Redshift clusters, can be launched inside your VPC. And so now clients in your home office can access these things over the private network. is things can access your existing data centers over direct connect connections to load data and to interact with existing applications. And there have been a ton of features that we've launched. With EC2, we didn't have a network to describe. There was no network. You had an IP address. And now that we have a network, we've added network features. So we started off with VPN and Direct Connect, private connectivity to the cloud. Security groups. We've always had security groups in EC2, but in VPC we added egress filtering. So if you want to filter packets outbound from your instances, you can do it in VPC. Network ACLs. We have a lot of customers that are used to grouping instances together. In EC2, IP addresses were random numbers. Two IP addresses that were close together didn't mean that they were doing the same job. They weren't both web servers. They might not even be owned by the same customer. In VPC, you can lay out your subnets however you want. If you have IT policies that say that these kind of servers must be separated from those kind of servers, you can do it with a couple of API calls, and then you can use network ACLs, as you do today in your data center, to separate those servers. Routing tables. This allows you to implement virtual appliances. With elastic network interfaces, we like our elasticity at AWS, you can basically plug multiple NICs into an EC2 instance. And so once you have two NICs in a box, you can set it up as a virtual appliance. You can plug it into two subnets, and now you've got a firewall or a load balancer or whatever it is that you want to program that box to do. Multiple IP addresses per NIC. We had customers that wanted to serve multiple sites off of their instances, and they didn't have SNI support, so they needed to serve different certs based on who was contacting them. Things like this are really useful to customers. And a fun one that we launched recently, I'm really a fan of this feature, is S3 endpoints. Prior to launching this feature, if your instances wanted to talk to S3, they had to do so over the internet. You had to create an internet gateway in your VPC, and you sent the traffic out. This meant that either this instance or a NAT instance, something had a public IP address, and this traffic was traversing the Amazon border network. So we introduced the ability to create an S3 endpoint. You declare this via our APIs. You say, I want an S3 endpoint, and I want to attach it to this VPC. And it's a routable target. And so your instance talks to your S3 gateway, your S3 endpoint, and the S3 endpoint takes care of getting that traffic to S3 via Amazon's private network. And the way we implemented this should look very familiar. We added a new kind of route. So rather than routing a CIDR block, you can now route what we call the named prefix. So there's a set of IP addresses that represent S3, in this case in US East 1. And you can say S3 in US East 1 doesn't go towards the internet, it goes towards there. And so exactly the same thing. It's a little bit more constrained. I assume you're not going to be sending UDP or ICMP traffic to S3. You can if you want. We're not going to do anything useful with it. We can wrap that packet, send it to an edge, and pass it on. And what we've done here is we've created a new encapsulation that's specific to VPC endpoints. And we don't NAT. When this packet arrives at S3, it has the original source IP address, the private IP address of that instance when it gets to S3, and it also has that green header there. It's tagged with the VPC endpoint ID. And the reason we created a new encapsulation was to decouple state. We didn't want S3 to have to understand all of the placement of instances. This doesn't tell you where the physical server is located in the VPC network. It just tells you it came from this VPC endpoint. Allows our two teams to iterate separately. We weren't coupled. So because you get the original source IP address and you get the VPC endpoint ID, you can do some interesting things. You can apply an Aspen policy, a standard AWS access control policy, to that endpoint, and you can say, only this bucket is accessible via this endpoint. Instances that are routing through that endpoint will not be able to get to any other buckets. Likewise, you can apply a policy to your S3 bucket. You've been able to do this for years. But now you can speak to the VPC endpoint or the VPC ID in the policy. And so I've said that my bucket is only accessible from this one VPC. I could give you my AWS keys. I could crack open everything else about that bucket, but you still wouldn't be able to get to it unless you were inside my VPC. And so now you can use the exact same policies that you use elsewhere in AWS to enforce your desired security stance end to end. So there's a spectrum here. On the one hand, you've got simple. On the other hand, you've got complex. Simple things tend to be limited. There are fewer knobs to turn, fewer dials to play with. Things that are complex tend to be more flexible. There's more of a learning curve. Well, the EC2 network was simple. You got an IP address, you got a public IP address, you were done. The VPC network is complicated, but there's a lot more you can do with it. And this isn't a value judgment. I own both a multimeter and an oscilloscope. They're both good tools, but I use them for different things. And so a feature that we added a couple of years ago is default VPC. The problem we had is we want everyone to be in a VPC. If you launch an EC2 instance, it's a perfectly reasonable thing to do. We like it when people launch EC2 instances. And you decide 3 years later that now your scaled application needs private connectivity somewhere, or you want egress filtering on your security groups, or you want an S3 endpoint. You have to move into a VPC. This is hard to do. So we wanted everyone to have a VPC, but we didn't want everyone to have to deal with all of the complexity of VPC on their first day as a customer. And so it needed to be code compatible with EC2. Like, we've got a getting started guide. We can fix our getting started guide. We've got an SDK. We can fix our SDK. There's an infinite number of blog posts out there that talk about how you do something in AWS. And we couldn't invalidate that whole body of knowledge. It had to continue working. So we had to be code compatible with EC2. And so it is. You can launch and terminate instances. You can run those shell scripts you find on web pages all over the place, and it works. But if one day you decide you need the functionality of VPC, you can break the glass. You can peek at the man behind the curtain. And it turns out that when you launched that first instance, we created a VPC, we laid out subnets, and then we hid everything from you. And so the getting started guide is still pick an AMI, run an instance. But if you later want connectivity to your home office or to your data center, you can go through all of that. And so we've managed to span a fairly large swath of this spectrum. We've got one service that allows customers to get started easily and quickly, just like EC2 did, but allows them to evolve incrementally as they need the additional flexibility, additional functionality of VPC to address some very complicated use cases. So thank you for your time. And I've been told that my return ticket home is in danger if you do not fill out your evaluations, so please fill out your evaluations. We value your feedback.